Okay, so welcome to our next session. So to have a recap, we had actually discussed the main branches of geology. So I think we have ended up with structural geology. So we discussed on some geological phenomena like faults, and some details on it. So as part of the structural geology actually is unconformity. So aside from the faults, today we are going to discuss also the another structural geology. We have the unconformity. It is actually a buried erosional or non-depositional surface that separates two different age rock masses or strata, indicating that the deposition of sediments was not continuous. The older layer was generally exposed to erosion for an interval of time before the younger layer was deposed, but the term is used to describe any break in the sedimentary geological record. So unconformity is just actually showing the the time gap between erosion and deposition. And as we all know, erosion is a movement of geological material from one place to another because of some geological agents like the wind, um, water, and some glaciers, and etc. So later on we will move on to details about geological agents, and then at some point it will settle on a certain location. That is what we call deposition. So the study of the structural geology and conformity reflects the time gap between those erosion and deposition. So the layers of rock can be investigated, what type of unconformity uh, between and among the layers. So we can see here, perhaps we can have here the slideshow. So the types of unconformity, first we have non-conformity. So as we can see on the simple diagram, we have the pink and yellow. So the pink represents the rocks. Okay, so it is a solid one. So it is an overlying crystalline. Okay, so sedimentary rocks are on top. So when we say sedimentary rocks, those are a more um, finer rock or smaller pieces of rock turned into sediments. And those rocks are prone to movement. Okay, so that is why we can see here uh, solid boundary on the bottom portion of the diagram. And then we also have here the angular conformity. So we have flat-lying sedimentary rocks, overlying tilted sedimentary rocks. So the tilted sedimentary rocks are actually the result of geological phenomena that was discussed before, like faults. Okay, so it was subjected to a faults or some type of movements, okay, because of the plate tectonics. And then we also have this conformity. So this conformity is a phenomena wherein an erosional surface separates sedimentary rocks from the older sedimentary rocks. So both layers are sedimentary rocks, only that the older one will tend to settle at certain location, especially on the lower portion of the layer. That is this conformity. Okay, so when we have a paraconformity, There is no visible ball gap in time, but ages above and below the paraconformity often determined by fossils. So, the fossil remains will just dictate the gap in time, because we cannot recognize actually the time gap between and among layers of paraconformity. So as we can see here, it is almost we cannot recognize the loose particles because almost they are of uniform compaction as well as placement. Okay, so that ends the structural geology. So now we are going to relate it to the engineering profession or civil engineering profession. So of course, geological structures modify the inherent physical characters of rock, rendering them more suitable or unsuitable for civil engineering purposes. As an example, it is undesirable geological setup for a dam having a downstream material of sedimentary rocks. What does it mean? So, for the purpose of a barrier in a river, of course, dams are constructed, and that is purposefully to, of course, generate um, current through the flow, and then, of course, the distributing water through channels, channeling it to some farmlands or for uh, communities utilities like drinking water, etc. And if we know geology, we can avoid actually a setup for a dam that is having a massive siltation problem, because as we all know, dams are prone to siltation, especially on the downstream. So imagine that on the downstream portion of the dam, wherein the the water will supposedly uh, flow into its purpose, like generating a turbine or distributing to households or some farmlands. It will be avoided because silt will be trapped on the downstream of the dam, and when that happens, it will accumulate some waste or pollution like gravel, heavy metals, some debris came from some erosion, and then logs. Of course, it will be trapped on the downstream, and then eventually it will pollute your river. And of course, it will affect the turbidity of your water or the quality of water. It will no longer be feasible to uh, utilization of some households or community. Hence, it will be polluted in a sense that uh, habitants will no longer be feasible because yun nga, if the flow will be prevented out of the siltation, okay, uh, yung turbulence ng river will be prevented also, of course. Essentially, in a river to survive, it needs to be flowing. Remember that flowing generates oxygen that is essential for living, even if on marine animals or fishes. Okay, that's so important in structural geology. So we move on to another branch, which is classified as main also. We have here stratigraphy. It is a branch of geology concerned with the study of rock layers, strata, and layering or stratification. It is primarily used in the study of sedimentary and layered volcanic rocks. So this is a geology that deals with the origin, composition, distribution, and succession of strata. So it is quite related to the unconformity, because unconformity presents the layers of the rocks. Okay, first, strata means layers. So actually there are laws uh, pertaining to stratigraphy. That is one of which is Stenos laws. So number one, the law of superposition. So it simply means that younger layer of rocks sits atop of the older layers. Okay. And then secondly, we have original orientation and orientation after tilting or folding. So this is the before and after of the layer. So the original horizontality layers of sedimentary rock are originally deposited flat. Okay, but because of some movements, because of mantle convection caused by the plate tectonics, of course, uh, the surface of the earth or the lithosphere will tend to move or subject to some tilting. Okay, so the third one is law of cross-cutting relationships. So it simply means that an intact layer would have, say, AB, and at some point there will be a different layer or unconformity. So letter C is just actually an intrusion of a certain mineral formation that disturbs them. Okay, so it could be a mineral formation, or it could be attributed to rising up of the molten material or melted material. Okay, so the fourth one, we have law of lateral continuity. So it simply says that layers of rock are continuous until they encounter other solid boundaries that block their deposition, or until they are acted upon by agents that appeared after deposition took place. So some intervention along the uh, development of these layers, like erosion and deposition, geological agents, are the intervening factors that tends to block. Okay, so therefore there will be no there will be a breakage on the continuity or lateral continuity of the rock layers. Okay, so stratigraphy in civil engineering profession, in selecting supporting soil for an engineering structure, the hardest layer is the most desirable one, of course. So kung magko-construct tayo, especially high-rise building, we really need to conduct a soil investigation. So one of the parameters of the foundation is actually the soil bearing capacity, and essentially we need to know the layers of the rock. Okay, whether you're putting a multi-story on the land, or you're putting a uh, bridge structure on the middle of the river, we really need to get the hardest point or the hardest strata, and that is why we really need to study stratigraphy. uh, it, it is actually establishing the most stable and competent foundation of the structure. Hence, the study of stratigraphy can also be utilized to predict underlying strata of a specific site. So actually, there are a lot of products of research wherein uh, the strata could be identified through some methods by not further um, investigation. That simply means you can predict out of the product of researches. Okay, and there so far it is feasible naman, ano, in determining the layers of the foundation. Okay, so another main branch of geology, we have paleontology. So although this is not so important in our endeavor, of course, Paleontology is the study of fossils, and fossils are remains of plants, animals, or the living organisms that have been replaced by rock material or impressions of organisms preserved in rock. Actually, paleontology have brought a significant contribution on the history on life of Earth, as well as the previous geology of the Earth, because as I have said before that geological structures are not permanent, and uh, geologic locations will tend to change. The geology will change, or the geological features will change, as well as the uh, climate will change because of geological features. And paleontology has significant uh, contributions in some of discoveries. Okay, paleontology in civil engineering professions. Of course, we can rarely found fossils, but they are great information, and such could be of significant consideration for civil engineer to recognize them. So, halimbawa lang na itsamba na merong fossils on a certain site. Of course, your action is to subject it to a more technical investigation. Okay? Tawag ka ng paleontologist or archaeologist and a geotechnical engineer as well to further investigate uh, kung kaya ba nung foundation, or what will be the measures in order to improve your supporting soil. Okay, so as we can see here in the picture, some of the fossil discoveries. And fossil discoveries, yung age, okay, can be determined, the history of the erosion, the deposition of some layers of the earth. So that could be dependent on fossil discoveries. So another main branch is the economic geology. So it is actually concerned with earth materials that can be used for economic or industrial purposes. These materials includes precious and base materials, non-metallic minerals, construction-grade stone, petroleum, natural gas, coal, and water. So this is actually more on the extraction of our resources out of the geological materials, such as metals, grade stones, petroleum, natural gas, etc. Okay, economic geology in civil engineering profession, relating it to our civil engineering profession. So it's not much of importance, since the study is more focused on understanding details on economic mineral deposits in terms of their mode of formation, occurrence, classification, association, varieties, concentration, properties, uses, etc. However, some of the topics would be supplemental to some civil engineering works, like cutting of slopes for roads and tunneling as well. Okay, so we move on to the specialized sciences, which advances geology in allied fields. So, geological knowledge will give birth to some specialized fields wherein it will bring a significant contribution on engineering works. Okay, um, we have actually around 11 specialized sciences enumerated here. So this time we are going to have a discussion on the first 5, and then the other allied fields will be discussed on the next lecture. So starting with geophysics. So it deals with physical processes and physical properties of the Earth. So the main major elements of the study, number one, so of course we have to deal with the shape of the Earth. So shape of the Earth. So it is very basic. The shape of the Earth is a hemispherical. And then we have a gravitational force of the Earth. Then magnetic fields of the Earth's internal structure, the Earth's composition, and then plate tectonics, so volcanic activity, the rock formation, and we have water cycle as well as fluid dynamics. So moving on to geochemistry. So this is the second allied. We have geochemistry. It is the science that uses the tools and principles of chemistry to explain the mechanisms behind the major geological systems such as Earth's crust and its oceans. So its study has also made significant contributions in understanding processes within and even beyond Earth's settings, okay, such as mantle convection, planet formation, and the origins of granite and basalt. So mantle convection, of course, this was already discussed in your plate tectonics, or the brief introduction on the plate tectonics. So as we all know, we have a hot layer beneath the lithosphere, or the surface of the Earth. Okay, so there are okay, the best way to explain this mantle convection is that the hotter material will go up and the colder material will go down. Why go up? Because if a certain matter is subjected to high temperature, it will loosen. Okay, it will loosen its the compaction, or the spacing of the molecules. Okay, and by that it will make it lighter. That is why the hotter material will go up and the cooler material will be denser, or will be heavier, or will be more compact molecules. So that is when that happens, there will be a movement on the underneath layer, okay, the asthenosphere, and the lithosphere is actually riding on the asthenosphere. But because of this, there are some structural or geological structure that will be formed, okay, and eventually it will cause a lot of deformations on the Earth's surface. So that is the mantle convection all about. Okay, so let me show here a certain diagram on geochemical cycle, so that you can appreciate the subject geochemistry. So of course, when the Earth is formed, there will be an original layers. Okay, out of that, there will be a land, and there will be a body of water, a land and water. And this land and water, there will be an inhabitant, or animals, plants, so vegetation. So this is where uh, they are living on the biosphere. Okay, so the Earth will compose of biosphere, hydrosphere, and atmosphere. So on biosphere, there will be a two-way link on biosphere to that of the atmosphere, and biosphere to that of the hydrosphere, and then biosphere to that of the soils. Of course, the biosphere the flow to the other link, like atmosphere, hydrosphere, and soils, the decaying of the animals or the plants that will be decayed, it will be degraded or deposed on bodies of water, oceans, lakes, rivers, or groundwater. It could be also deposed on the atmosphere through some form of gas like carbon dioxide and methane. And biosphere, from biosphere, it will decay and it will um, be mixed with the soil. Okay, so that's it. All of those are some chemical processes, and then the soil will be linked to the hydrosphere through runoff because of the geological agents. So those are some possibilities, and then soil will return back to biosphere by what process? Assimilation. The same true with the hydrosphere. Some of the uh, components will assimilate going back to biosphere through geological agents again. And then atmosphere will have a photosynthesis, which is of course essential for um, inhabitants like plants. Okay, so those are the process. And then biosphere will be also directed, has a direct link to lithosphere, and lithosphere is the Earth's crust. It will have also a link to the hydrosphere as through the form of erosion. Okay, so aside from this surface of the Earth going on regarding geochemical cycle, it is also linked to the deeper layer of the Earth through subduction and through the exit through volcanism. Okay, and then for the outer space could also have a contribution to the surface of the Earth because the meteorites, yun daw ano there are some stories, researches that the meteorites has a lot of um, influence on the Earth's materials like metals, the formation of metals. Okay, so before at this Stone Age, hindi pa nila ginagamit ang metal, so meaning siguro wala pa silang resources, and after some time there are some meteorites. They can now extract some of the minerals of the meteorites and form it as a metal. Okay, so that is the contribution of the extraterrestrial agent. Okay, so moving on to geohydrology. This is another allied science. So it is a science that deals with the character, source, and mode of occurrence of underground water. So it deals with how water gets into the ground. So it will have a recharging, how it flows in the subsurface through aquifers, and how groundwater interacts with surrounding soil and rock. So here we can see a simple picture of geohydrology. So aquifer is actually the accumulated groundwater. Okay, so we have two types. We have a confined aquifer and the unconfined aquifer. So more quality can be found on under confined aquifer. So we can see here that the unconfined aquifer could directly catch the surface water through permeability. Okay, so we have here also between the confined aquifer are confining beds, which has low or very low hydraulic conductivity. So when we say hydraulic conductivity, it is a measure of how fast water will penetrate to a certain material. So if we have a confining bed there with the low hydraulic conductivity, so it would take certain years, like centuries or millennia, to penetrate the confined aquifer. Okay, and that is the discharge area out of the what we call catchment area, or in mountainous terrain we have watershed area. Okay, and aside from the watershed area for recharging purposes, there are also exit points like the stream or those are the discharge area. Okay, so another allied science on geology is glaciology. Of course, we are familiar with the term. It is the scientific study of glaciers, or more generally ice, and natural phenomena that involves ice. A glacier is an extended mass of ice formed from snow falling and accumulating over a long period of time, and then glaciers move very slowly, either descending from high mountains as in the Valley of Glaciers, or moving outward from centers of accumulation as in continental glaciers. So this time let me revisit you on the video on glaciers so that you can appreciate glaciology. So let me play the video.
Let's take a look at glaciers. What exactly are glaciers? Glaciers are simply bodies of ice that form from repeated periods of snowfall. Once they form, they are pulled very slowly downhill by gravity. There are generally two types of glaciers. First, we have alpine glaciers, which form high up in the mountains and travel downhill like rivers of ice. Then we have continental glaciers. These are massive glaciers that cover entire land masses, and they tend to move outwards from the center, often towards the coastline. Let's see what these look like. Here's an alpine glacier, and you can see it looks just like a river of ice. All of these flowing slowly downhill, carving out the rock as they go. A great example of a continental glacier would be Antarctica. It's this huge, thick sheet of ice that covers virtually the entire landmass. We see a similar thing in Greenland. Up close, you can see these huge sheets of ice ooze out from the center towards the coastline, slowly grinding away the rock beneath. When either type of glacier, whether it be alpine or continental, when they reach the ocean, large chunks of the ice tend to break off, and this is a process that's known as calving, and you can see it happening here. As climate change continues and the atmosphere and oceans are warmed, calving is happening at a faster rate. These big chunks that fall off of the glaciers then float out into the sea, becoming icebergs. The most important thing to look at with glaciers is how they impact the landscape. That is, how do they change the land as they grind over the surface over millions of years? First and foremost, we should know that glaciers grind down the rock that's on both sides and on the bottom of the area where they're moving, and the result is this large U-shaped valley, which you can see here in the diagram. Notice it's shaped like the letter U. Here's what it looks like in reality. we can infer that this valley was formed by glaciation at some point in the past, and that inference is based on the general shape of the valley. Here's another U-shaped valley. As glaciers grind over the bedrock, they scratch it. They leave behind marks and grooves that are called striations. And these striations are important because they reveal the direction that the ice was moving before it melted. You can see them plucking and grinding away at the rock beneath, resulting in something like this. And by looking at those striations, we can draw an inference about what direction the ice was moving. And we see them here as well. When a glacier melts, it's going to deposit or drop off all of the sediment, all of the pieces of rock and sand and silt and clay that it was carrying with it. And when it does so, it just kind of drops it off. And so we end up with these big piles of this unsorted and unlayered sediment. And we have a term for these sediments, and that's called glacial till. Here you can see big, small, all mixed together. And this is what it looks like in reality. And this serves as further evidence that there was once a glacier in this area. When the glaciers move, they push this till or this unsorted sediment out in front of them, very similar to a bulldozer pushing a pile of soil. When the glaciers then melt, they leave behind these piles of sediment, and these are called moraines. Moraines reveal a lot about a glacier. Particularly the terminal moraine, shown in this diagram, line XY, this marks the farthest point that a glacier traveled before it receded or melted away. Here's a terminal moraine in reality. This area right here is the till, the unsorted, unlayered sediment that was pushed out in front of the glacier. We can see another terminal moraine right here. Long Island, New York is a great example. It is formed as a result of multiple periods of glaciation, and therefore there are multiple terminal moraines, the Harbor Hill Moraine, the Ronkonkoma Moraine, etc. If we were to look at line EF here from the side as a profile, it would look like this. You would have this first moraine, and then notice this term outwash, which is just some of the material that's been washed out by melting water. And then we have a second period of glaciation that resulted in the Ronkonkoma moraine. Glaciers are the only agent of erosion that are really capable of moving large boulders. These are called glacial erratics. So when we see randomly scattered boulders throughout the landscape, we can infer that they were moved there by a glacier. And that's because running water or wind are not capable of moving such large sediments. So here's a glacial erratic, and here's what they look like in reality. The only way these sediments could have gotten there is by being transported by a glacier, frozen in a large sheet of ice. Oftentimes, glaciers will leave behind something called a drumlin, which is simply an elongated hill of sediment. Remember, the sediment would be unsorted and unlayered. What's interesting about drumlins is the shape that they often take as the ice goes up and over and moves the sediment. You end up with this teardrop-shaped hill. And by looking at the shape of the hill, you can determine the direction that the ice flowed. It often flowed towards the flatter side of the hill, the less steep side. Here's a field of drumlins in upstate New York, and by looking at the shapes, we can tell that the ice was moving in this direction. Here's an entire community that appears to have been built right on top of a drumlin, surrounded by farming fields. This diagram shows us the stages in the formation of what's called a kettle or a kettle lake. And this is very common in areas where you've had glaciers. What happens is large pieces of ice break off from the glacier, and then that ice gets buried by some sediment and then eventually melts, leaving behind a hole in the ground known as a kettle. And if it fills with meltwater, it'll be a kettle lake, as seen here and here. When the glaciers melt, we get a lot of meltwater, which forms streams coming off the front end of the glacier. Like all running water, these deposit sorted sediments. So remember, the sediments deposited by the glacier itself are unsorted. That's our till, creating our moraines. But when we have outwash, when we have water that's become liquid and melted, creating streams, then we end up with some sorted sediments. And you can see that in this diagram here. This is an outwash plain, so all of these sediments were deposited by runoff from melting glaciers, also seen here. If we look at New York State, many of the features we see were formed by glaciers during the last ice age, which was about 22,000 years ago. Here we see the movement of the various glaciers during that ice age, all generally moving from Canada down south. We can see lots of features in New York State that have formed as a result of glaciation, including these large fields of drumlins near Oswego, right off of Lake Ontario. Additionally, we see the Great Lakes, which were actually just large U-shaped valleys that have become dammed by sediment and then filled with water, very similar to the Finger Lakes of upstate New York, all the result of glaciers. As climate change continues and the planet warms, including the oceans and the atmosphere, we're starting to see the disappearance of large-scale glaciation. If you look at this comparison of the same spot, 60 years apart, you'll notice that the majority of the ice has disappeared. The same thing can be seen here, and we're seeing this happen all over the entire planet. As the ice melts, it adds fresh water to the oceans, causing sea level to rise, which is further complicating our complex atmospheric weather conditions and how climate works on a whole. It's something that scientists are exploring and trying to figure out a solution for as we speak. That's a quick look at glaciers. Thanks very much.
Okay, so I hope that the video helps on glaciology. Okay, so another allied branch is seismology. Of course, the ancient Greek seismos, meaning earthquake, or the study of the earthquakes, the propagation of elastic waves through the earth, or some environmental effects like tsunamis, so as well as diverse seismic sources such as volcanic, tectonic, glacial, fluvial, oceanic, atmospheric, and artificial processes such as explosions. A related field that uses geology to infer information regarding past earthquakes is paleoseismology. So a recording of earth motion as a function of time is called a seismogram. So a seismologist is a scientist who does research in seismology. So before we end our lecture, we need to view first this video for you to appreciate again one of the allied branches, which is seismology.
Earthquakes are the result of uncontrollable geologic forces. Their effects can range from gentle, even unnoticed motions, to devastating and violent ground shaking. Few of us have experienced such shaking, but we have all heard news reports of the damage that results from ground motion or secondary phenomena such as liquefaction or triggered tsunamis. The science of seismology has begun to answer some fundamental questions about these events. Why do we have earthquakes? How do earthquakes and related phenomena happen? What causes the ground to shake? And how do we measure earthquakes? To address these questions, we'll take a look at the roles of plate tectonics, mechanics, seismic waves, and magnitude and intensity. To understand why we have earthquakes, we need to step back for a big picture view of the entire Earth as a system. To understand the role of plate tectonics in the system, we can divide the Earth into four main compositional layers: the crust, mantle, outer core, and inner core. Convection currents are generated as part of the Earth's cooling process, with heat rising and escaping to the surface and cold material sinking. The Earth's solid inner core spins slowly, cools, and radiates heat. The liquid outer core convects, generating the Earth's magnetic field and transferring heat to the mantle. convection of the mantle is driven by cooling forces from above and heating from below. Heat is produced from within by the decay of radioactive elements. A rigid, cooled outer layer of the Earth, consisting of the crust on top of a thicker layer of stiff, cooler mantle, forms what we call the lithosphere. The convection currents exert push and pull forces that break the lithosphere into mobile sections we refer to as tectonic plates. Earthquakes rupture the active boundaries of these plates as they grind past, under, and away from each other. This simulation shows the last 200 million years of global plate tectonic motions. Notice how the plates break apart and move about, eventually arranging themselves into the continents as we recognize them today. At transform boundaries, plates slide past one another and form strike-slip faults. At convergent boundaries, continents collide and form mountains, or one plate slides beneath another and forms a subduction zone. At divergent plate boundaries, plates move apart and form rifts within continents or mid-ocean ridge spreading centers in the oceans. To understand how earthquakes happen, we must examine the mechanics of the forces and motions affecting plates and their interactions with one another. You are viewing two oceanic plates moving away from a spreading center. In cross-section, we can better see the convergence of plates at subduction zones and the divergence of plates at a mid-ocean spreading ridge or a rift valley. Although the plate motions are generally smooth, the mechanics of earthquakes arises from the friction at the plate boundaries. Faults held by this friction remain stuck for long periods of time and then suddenly break in major earthquakes. There are three main types of faults that are associated with the three types of plate boundaries. Normal faults are generally found in divergent plate boundary zones, where the plates are pulling apart from one another due to extensional forces. They release less energy or cause the weakest shaking of all the fault types. Thrust or reverse faults are generally found in convergent plate boundary zones, where plates collide with one another and experience compressional forces. These faults cause the largest earthquakes. Strike-slip faults are generally found in transform zones, where the tectonic plates slide horizontally past each other, creating parallel shear forces. The San Andreas Fault is an example of a strike-slip fault. If a subduction zone earthquake occurs along an underwater thrust fault, the associated uplift can displace a huge volume of water. The resulting wave is known as a tsunami. Earthquakes on any type of fault follow a similar pattern. When the stress reaches the breaking point on a fault, a rupture begins at the hypocenter and continues to break along the fault surface. The epicenter is the geographic location at the surface of the Earth directly above the hypocenter. To grasp what causes the ground to shake, we need to understand the propagation of seismic waves. Just as throwing a rock into a pond causes radiating ripples, rupturing of a fault in an earthquake causes a transmission of energy in the form of seismic waves traveling away from the hypocenter and epicenter. Earthquakes produce many types of seismic waves. Body waves travel through the Earth, and surface waves travel along the Earth's surface. It is the arrival of seismic waves that people feel when they experience shaking in an earthquake. Body waves can be broadly classified in two categories. The P wave, or primary wave, is a compressional body wave that alternately compresses and expands the particles that it moves through within the Earth. P waves can pass through any medium, and so travel through every layer of the Earth, and even the air, like sound waves. The S wave, or secondary wave, is a body wave that travels through the interior of the Earth with a shearing motion. S waves cannot travel through liquids, including the Earth's liquid outer core. There are likewise two kinds of surface waves. Rayleigh waves have energy that causes the ground to roll up and down, like water waves on the ocean. Love waves move the ground from side to side and are similar to shear waves, but can have larger amplitudes. Seismic waves carry the energy from the earthquake source to the surface where people can feel the shaking. Methods for measuring earthquakes quantify earthquakes and their effects. The magnitude scale measures the size of different earthquakes, independent of where the seismic waves were recorded. The larger the magnitude, the larger the offset and the area of fault that moved in the earthquake. Also, for large earthquakes, the shaking is stronger and lasts for a longer time than for small ones. Each whole number step in earthquake magnitude represents an increase in amplitude of ground motion by a factor of 10. In a magnitude 6 earthquake, for instance, the ground shakes 10 times as much as in a magnitude 5. And in a magnitude 8, the ground shakes 1,000 times stronger than in a magnitude 5. In terms of energy, the increase is even greater, with each step in magnitude having approximately 32 times the energy of the previous. For instance, a magnitude 6 releases about 32 times the energy of a magnitude 5, and a magnitude 8 releases around 32,000 times the energy of a magnitude 5. There is no upper limit on magnitude. However, the largest recorded earthquake in history was a magnitude 9.5. Earthquake magnitude does not vary from place to place, but is a characteristic of the total energy released by a particular earthquake. It is also helpful to use an intensity scale to quantify ground shaking due to the earthquake. The shaking intensity can vary depending upon distance from the hypocenter and local geology, and is a better measure for assessing damage risk. This is the shake map for the magnitude 6.7 Northridge earthquake, which occurred on January 17, 1994. The areas that experienced strongest shaking are in warm colors like red, versus areas of mild shaking in cooler colors like blue and green. Ground shaking recorded by seismic sensors is used to make the shake map. We can also make subjective intensity maps based on reports from local people from each area through online resources like the Did You Feel It USGS webpage. We have earthquakes because tectonic plates grind past, under, and away from each other and generate earthquakes at their active boundaries. Through seismological research, we can better understand and measure the seismic waves traveling from earthquake sources that cause ground shaking and potentially preventable damage. As much as we know about earthquakes, there is still much more to learn through continued earthquake research.
Okay, so I hope that the video helps. Of course, we have learned some of the terminologies, especially on type of waves. So ano may mga yun? P wave, S wave, Rayleigh waves, and love waves. So far the study of seismology is very much of concern because nowadays there are a lot of earthquake happening in our planet. Perhaps because it is the effect of some climate changes, because as you witness, there is a very a fast depletion of glaciology in because of climate change, and the extinction of glaciology, of course, will have some significant effects on geological processes. And because of a lot of structures, marami na tayong natatayong structures as of the modern times, these structures are very prone. Okay, so the more structure, the more damages that will be caused by the earthquake. So that is why, again, this seismic researches in engineering is so far of major concern for us to control the damages. Okay, we cannot really prevent the damage, but we can control the damage by the aspects of seismology. Okay, in particular the energy dissipation. Okay, the energy dissipation, we are going to design our structure considering this energy dissipation. So you might want to consider what is the most active fault nearest to your site. Okay, so actually there are some codes in structural codes pertinent to earthquake design. Okay, so our structure nowadays should be in earthquake resistant structure, should be designed in an earthquake resistant structure. Okay, so this ends our video lecture for today. I hope you learned a lot from this session, from the videos that was presented. And for the next meeting, you'll be expected to have a uh, quiz on what we have discussed on the first two presentations. Okay, so with this, we thank everyone for viewing this video tutorial and have a nice day. Thank you.